The universe, in its unimaginable scale, presents us with one of the most profound and unsettling questions of our time. Are we alone? On one hand, the sheer statistics seem to argue against our uniqueness. Our own Milky Way galaxy alone is home to billions of stars, and recent astronomical discoveries suggest that a significant fraction of these stars host planets, many of which are situated within the Goldilocks zone, the habitable region where liquid water could exist. The logic is simple. With so many potential homes for life, it seems almost arrogant to assume that Earth is the only one to have nurtured intelligent beings. This line of reasoning is what led the renowned physicist Enrico Fermi to pose his famous question in 1950. While discussing the possibility of extraterrestrial life with his colleagues, he simply asked, "Where is everybody?" This seemingly simple query encapsulates a deep and troubling contradiction known today as the Fermi Paradox. The paradox highlights the vast discrepancy between the high probability of extraterrestrial civilizations existing and the complete and total lack of evidence for them. This silence, often referred to as the Great Silence, is what truly fuels the mystery. Despite decades of dedicated listening through projects like SETI, Search for Extraterrestrial Intelligence, our most powerful radio telescopes have detected no definitive signals, no broadcasts, no signs of life from beyond our solar system. The universe, to all of our senses, is silent. So, how do we reconcile the expectation of a universe teeming with life with the stark reality of this profound silence? One of the most compelling and chilling explanations is the Great Filter theory. This theory suggests that at some point in the evolution of life, there exists a formidable barrier, a filter, that is exceptionally difficult for life to overcome. This filter could be a single, catastrophic event, or a series of incredibly unlikely evolutionary steps. If it lies in our past, we are one of the rare few who have made it through. If it lies in our future, the silence of the cosmos may be a terrifying omen of what awaits us. This video will explore a specific and fascinating possibility, that the Great Filter occurred right here on Earth, billions of years ago. It's a possibility rooted not in cosmic catastrophes, but in a microscopic, biological event that was so rare, so improbable, that it may be a universal bottleneck. We will investigate the compelling argument that the genesis of the complex eukaryotic cell represents this very event, a crucial and perhaps insurmountable hurdle that most life in the cosmos never manages to clear. Earth's ancient history is a tale of two distinct eras. The first era began with a burst of promise, a remarkable demonstration of how readily life can spring into existence. The second era, however, was marked by an eons-long delay, a period of apparent stagnation that holds a crucial clue to the Great Filter. Looking back at our planet's early geological record, the timeline of life's origins is surprisingly swift. After Earth had cooled enough to form a stable crust and oceans, evidence from ancient rocks indicates that life appeared very quickly, within just a few 100 million years of the planet becoming habitable. Simple, single-celled organisms, known as prokaryotes like bacteria and archaea, were already thriving. The oldest fossil evidence, found in rocks dating back roughly 3.7 billion years ago, suggests that the initial spark of life may not be an incredibly rare event. Given a suitable environment and the necessary chemical building blocks, the spontaneous generation of these basic microbial forms might be almost inevitable across the cosmos. For the next 2 billion years, Earth was a microbial world. These simple organisms dominated every corner of the planet, from the deepest oceans to the nutrient-rich shallow seas. They weren't just surviving, they were fundamentally altering the planet. Through photosynthesis, early microbial mats began to release a byproduct that would change everything: oxygen. This gradual transformation, known as the Great Oxidation Event, created an oxygen-rich atmosphere, a prerequisite for the high-energy needs of more complex life forms. The stage was set. The promise was clear. And yet, nothing happened. Despite the planet being bathed in life, and its atmosphere being primed with oxygen, the very fuel for advanced biology life remained frustratingly simple. For nearly half of Earth's entire history, from approximately 3.7 billion years ago to a little over 2 billion years ago, the only life forms on our planet were single-celled microbes. There were no plants, no animals, no fungi, no brains. This was a world of single-celled organisms, existing in a state of suspended animation on the evolutionary scale. Why this prolonged period, this great delay, suggests that the transition from simple life to complex life is not a simple, linear progression. The existence of a suitable environment and the building blocks of life are not enough. There was some kind of fundamental barrier, a missing piece of the puzzle that prevented life from advancing to the next stage. It indicates that something about the leap from a simple prokaryote to a more complex cell was a hurdle so high that life on Earth was stalled for billions of years. This barrier, this profound absence of complexity in a world ripe for it, points directly to the possibility of a filtering event. The next step in our story will explore what that crucial, game-changing step was. If the first 2 billion years of Earth's history were a quiet, microbial slumber, then the period that followed was a revolutionary awakening. Approximately 2 billion years ago, life on Earth underwent a pivotal, transformative shift that would permanently alter its evolutionary trajectory. This was the advent of the eukaryotic cell. The birth of the eukaryotic cell was not a gradual, incremental change, but a singular, dramatic event. The prevailing scientific theory, known as endosymbiosis, posits that this revolution began with an incredibly rare and improbable union. A larger, simple, archaeal microorganism engulfed a smaller bacterium. However, instead of being digested as food, the bacterium survived and entered into a symbiotic, mutually beneficial relationship with its host. This was a biological partnership unlike any that had come before. The sheer improbability of this event cannot be overstated. All eukaryotic life on Earth, from the smallest amoeba to the largest whale, is descended from this one ancient fusion event. This suggests the conditions required for such a successful and permanent merger were so specific, so rare, that it may have been a once-in-a-billion-years cosmic fluke. Why was it so difficult? The two organisms had to coexist without one destroying the other. The host had to find a way to tolerate the foreign genome of the bacterium, and the bacterium had to find a way to share its energy with the host without being completely consumed. This wasn't a simple chance encounter. It was the biological equivalent of winning a grand lottery. The bacterium, a microscopic powerhouse, eventually evolved into the mitochondria, the cell's energy-generating organelle. This breakthrough provided the new, composite cell with a colossal energy surplus that its simple ancestors could only dream of. The mitochondrion, in essence, was the engine that would drive all future complexity. The repercussions of this single event were monumental. Because all eukaryotic life traces back to this single fusion, it powerfully suggests that the conditions required for it to happen were not easily replicated. Other planets might have microbial life, but they may be stuck in the prokaryotic stage precisely because this crucial fusion never occurred. This new cellular structure unlocked capabilities that neither organism could have achieved alone. The new eukaryotic cell was significantly larger and more complex. It had a dedicated energy source, a sophisticated internal transport system, and the capacity to store and manage vast amounts of genetic information. This new, energy-rich environment was the essential foundation for everything that followed. The new cell's ability to produce significantly more energy than its prokaryotic ancestors was the key to unlocking complexity. It provided the power needed to develop a larger genome, complex internal structures like the nucleus, and eventually, the leap to multicellularity. Without this initial energy surplus, the creation of tissues, organs, and entire organisms would have been biologically impossible. The emergence of the eukaryotic cell was not just another step in evolution. It was the critical moment that opened the floodgates to all the complexity we see on Earth today. The emergence of the eukaryotic cell was not just a lucky accident. It was a fundamental shift in the very code of life. It marked what researchers refer to as an algorithmic phase transition, a concept borrowed from physics and computer science to describe a sudden and profound reorganization of a system's fundamental properties. To understand this, we need to look at the intricate relationship between genes, proteins, and the evolution of the eukaryotic cell. Early life forms, the prokaryotes, had relatively simple genes that directly coded for proteins. As life evolved, a clear pattern emerged. The length of genes increased. This was a straightforward, linear process. Longer genes meant the potential for larger, more complex proteins. which in turn could perform a wider variety of functions. However, this growth hit a natural limit. Research shows that protein size stabilized at around 500 amino acids. This is because at a certain size, proteins become unstable and difficult for the cell to manage. When protein size reached this upper limit, evolution had to find another way forward. The solution was brilliant and counterintuitive. DNA continued to expand, but it began adding sequences that did not code for proteins. This marked the start of the non-coding phase, a new evolutionary era, driven not by a simple increase in protein size, but by the complex regulation of when and how proteins are made. This transition from the coding phase to the non-coding phase appears to have happened at a very specific point. The critical threshold for eukaryogenesis seems to be a gene length of roughly 1,500 bases and a protein length of 500 amino acids. Once these values were reached, the system underwent a major reorganization. This is the phase transition. Think of it like the freezing of water. Water can be supercooled below 0 degrees Celsius, remaining a liquid in a state of potential energy. But at a critical point, a slight disturbance can cause the entire system to instantly reorganize into a solid, crystalline structure of ice. Similarly, life's genetic machinery, after billions of years of slow, incremental change, suddenly reorganized at this critical threshold, unlocking an entirely new level of biological complexity. It wasn't a slow build. It was a fundamental shift. The key to this reorganization was the advent of the nucleus and the inclusion of unlike prokaryotes, which have their DNA floating freely in the cell's cytoplasm. Eukaryotes evolved a protective nucleus to house their DNA. This physical separation was crucial. It meant that life could now split its genes into parts: the useful coding sequences, called exons, and the non-coding sequences, called introns. The beauty of this new system was that genes could now grow much longer by accumulating introns. The introns were spliced out of the genetic message, the RNA, before it was used to create a protein. This meant that the final protein recipe could be much more intricate, assembled from exons in different combinations, allowing for a single gene to create multiple types of proteins. This separation of transcription copying DNA to RNA inside the nucleus, and translation creating the protein outside the nucleus, gave life a new level of flexibility and control. It was no longer a simple, linear process. It was a sophisticated, adaptable system that allowed for greater regulation, more efficient evolution, and ultimately laid the genetic groundwork for all the complex life that followed. The nucleus introns and the sophisticated processing of genetic information were the ultimate outcome of this algorithmic phase transition. Our journey through Earth's history brings us back to the universe at large. Now, with a new perspective on the Great Silence, if the emergence of the eukaryotic cell was a great filter, a bottleneck so narrow that life struggled for billions of years to pass through, then the implications for the cosmos are profound and chilling. Based on our updated understanding, it's entirely possibly and perhaps even likely that simple, bacterial-like organisms are abundant throughout the galaxy. The rapid emergence of life on early Earth suggests that the initial steps from non-living matter to a simple microbe might be a common, almost inevitable event given the right conditions. This idea is supported by astronomical observations that show organic molecules, the fundamental building blocks of life, are widespread in interstellar space, found in nebulae, comets, and on the surfaces of other planets. It's plausible that many of the billions of habitable planets in our galaxy are indeed home to some form of microbial life. However, if the eukaryotic transition is the great filter, then most of these worlds would be frozen in the microbial era. They would be teeming with life, but it would be simple, single-celled life. There would be no complex creatures, no intricated ecosystems, and certainly no cities, radio signals, or technological civilizations. From a distance, these planets might even seem vibrant and alive. This distinction between simple microbial life and complex intelligent life is crucial. When scientists search for life on exoplanets, they often look for biosignatures, atmospheric chemicals like methane, oxygen, or carbon dioxide. While detecting these signatures would be an incredible discovery, it wouldn't necessarily mean a complex civilization exists. These atmospheric gases are far more likely to be the exhalations of simple, photosynthetic microbes. just as they were for billions of years on Earth. It would be a monumental discovery, but it wouldn't solve the Fermi Paradox. This perspective gives strength to the rare Earth hypothesis, which argues that the universe is not teeming with advanced civilizations, because the specific set of conditions required for complex, multicellular life is incredibly rare. The path from a simple single-celled organism to an intelligent being is not a straight road. It's a treacherous obstacle course with a series of difficult-to-pass filters. The rare Earth hypothesis proposes that our planet passed through a key filter that most other planets did not. The formation of the eukaryotic cell may be this very filter. It was a unique, low-probability event that opened the door to all subsequent evolutionary complexity. Therefore, the Great Silence may not be a sign that life is rare, but rather that the jump from microbial life to technological life is almost impossibly difficult. The journey from the Fermi Paradox to the eukaryotic cell offers a powerful and sobering explanation for the Great Silence. If the emergence of the eukaryotic cell was a great filter that only Earth passed, then our existence becomes not just a matter of cosmic chance, but an incredibly rare and significant event. If the eukaryotic revolution was indeed the bottleneck, then humanity's place in the universe is far more exceptional than we might have imagined. We are not simply one of countless civilizations. We are the outcome of a grand cosmic lottery where the odds were overwhelmingly against us. This perspective suggests that while the cosmos may be full of simple life, we may be among the very first or even the only ones in our galactic neighborhood to have made the critical leap to complex multicellular life and subsequent intelligence. Our ability to develop technology, to contemplate our place in the universe, and to search for answers to questions like the Fermi Paradox is an extraordinary consequence of this one-in-a-billion-years event. We are, in a sense, the universe's lucky exception. This exceptional status comes with an enormous responsibility. If we are the sole bearers of complex consciousness and technological capability in our corner of the galaxy, then the flame of intelligence rests entirely in our hands. We become the eyes, ears, and questioning mind of the galaxy, with a duty not only to understand our universe, but to ensure the continuation of our species. The path of human history has been fraught with challenges, and the potential for self-destruction, be it through nuclear warfare, climate collapse, or unchecked technological risks, is very real. The universe's Great Silence could be a silent warning that our future contains a filter of its own. Will we be the ones to light the first torch in a dark universe, or will we falter, joining the silent worlds of microbes from which we emerged? While the rare Earth hypothesis and the eukaryotic filter offer a compelling explanation, a truly scientific perspective requires us to consider other possibilities for the Great Silence. A high-quality exploration of this topic would be incomplete without them. The self-destruction hypothesis. This viewpoint suggests that civilizations inevitably reach a technological point where they develop the means to destroy themselves. Nuclear weapons, self-replicating nanobots, or even AI gone wrong could be the future filter that all civilizations fail to overcome. In this scenario, the silence is not due to a lack of life, but a lack of long-lived, intelligent life. The zoo hypothesis. This intriguing theory posits that advanced alien civilizations are aware of us, but have chosen not to make contact. They might be observing us, treating our planet like a protected nature preserve or a zoo, waiting for us to reach a certain level of maturity before they reveal themselves. Other filters and unknowns. It's also possible that we simply don't know what to look for. Maybe extraterrestrial civilizations communicate in ways we can't yet comprehend. Or perhaps there are other, even more subtle filters we haven't identified. The universe is vast and full of unknowns, and the true reason for the Great Silence might be a combination of several factors we are only just beginning to contemplate. In conclusion, the Fermi Paradox remains one of science's most enduring mysteries. But by looking inward at our own planet's history, we can find a compelling and scientifically grounded answer. The story of the eukaryotic cell is a testament to the fact that our existence is not a given, it is a miracle of low probability events, a rare jackpot in the grand lottery of cosmic evolution. If the silence of the cosmos is indeed a warning that the path to complex life is an incredibly rare one, then our existence holds a significance greater than we can imagine. We are not just a species on a planet. We may be one of the few torches of intelligence in the vast darkness of the universe. Our responsibility is to protect and nurture that flame, to ensure it doesn't flicker out. So, what are your thoughts? Do you believe the emergence of the eukaryotic cell was the great filter that we were lucky enough to pass? Or do you lean towards other hypotheses, thinking we are not alone, but simply being watched from a distance? Please share your thoughts in the comments below. If you found this video fascinating and want to explore more cosmic mysteries, be sure to like, share, and subscribe to the Astronomical Library channel for more content. Thank you for watching.